Okay, let's go for chapter 6 then for shaft and accessories parts. That what we're gonna go for. It's gonna be the keys then. Typically, the associate parts of the shaft is gonna be key, pin, and spile respectively. So typically, the things that what we're gonna cover with is gonna be the keys. The key gonna typically look like this, and anyway, see, the key is gonna be, the shaft is gonna be inside the insert between the hubs of the pulley, things like that. So therefore the key gonna insert in between the shaft and the hubs of the pulley respectively. So therefore this figure A is going to be show you type of the a key that will be employed on it. Typically, the standard keys that will be employed is going to be in A is going to be square key. Then what typically we're going to show you on it is going to be the view time W. You can figure out. We're going to employ the space the W over 2 in the hub, another W over 2 in the shaft respectively. And then for flat key is going to have W time H. So we're going to employ the space into the hub of H over 2, another H over 2 into the hub respectively. And then C is going to be round shaft. There's going to be round there. And then another one is going to Kennedy key is going to be left and the right. And then we have a wood draft key is going to be, this is the front wheel, this is the, the along the side wheel. See, this is going to be sometime in Thailand we call it Lim Wong and things like that. Okay, this is a German type that what we employ a lot for wood draft keys ever. This is the cross section type, things like that. See, so this one we employ in the space of that. Okay, and then another one is gonna be the keep head keys. This is the things that what we apply on it. We have a keep head here, so easy for this assembly. And we put along the side. We just have a keyways along the head to the toe, things like that. And then feather key, we're gonna have some kind of like a screw to fix up the keys just on the keyways or the shaft, things like that. Okay, so therefore the things that I explain exactly the same thing that what I just have written down there. So the key is typically employed as a standard things that what is shown here. So in table 6.1 show the standard and its corresponding shaft diameter. Typically the size of the key is dependent upon the shaft diameter, things like that. So therefore, the smallest shaft diameter is going to be employed for the wood draft key. You may figure out, see, if 3 to 4 millimeter, we're going to go for a wood draft key. See, and then for the smaller key, just like 6 to 7, things like that, we're going to have a rectangular or square key, things like that. 2 by 2, and then the flat key just follow up, look like that all the way. And then it's going to employ the um, some kind of wood draft key up to a certain diameters there, okay, up to beyond 38 to 44, things like that. We never ever employ the wood draft key anymore because it's why is it going to be some kind of bigger sharp diameter. We like to employ more torque on it, so therefore we never employ that wood draft key anyway. So we're gonna employ for some kind like a square key on flat key rather than that anyway. See, so this is going to be the standard key that what we just applied on it. And then the length of the key that we recommended is going to be the size is going to be recommended to be like this anyway. So therefore, this is the shape of the square key and the wood draft key. They have their own dimension according to the dimension that what they have the B, H1, R, and T1 and T2 respectively. That what they have their own dimension, look like that. Okay, for the keys. That's corresponding on that anyway. For the design of the keys, okay, we're gonna have the compressive stress, okay, because it's where we assemble the keys into the keyways, things like that, and we have the shear stress on the key itself, things like that. See, you may figure out in there. So figure 6.2, in case just we employed a wrong keys into the keyways, things like that. See, the areas of contact is going to be a point rather than in terms of a full scale, things like that. See, it's going to be a point of that. It's not good anyway. So this kind of thing is going to mislead to employ a good one, things like that. So what we call is loosely fitted key, things like that. If in the proper manner, it's going to be in 6.3 is a good manner, things like that. So it's fitted all the way, things like that. F1 is on the side, and F prime is going to be on the top part, the bottom part, respectively, and we have a torque applied on it, even on the shaft itself as on the pulley itself. See, pulley is going to be on the hub of the pulley itself. Okay, so therefore, if just like that, see, we find a relationship of the figure 6.3. See, therefore, the relationship of the horizontal force of F and the shaft torque is going to be torque is equal to F times DOH plus H over 4 force times the arms. Okay, since H over 4 is very small, we just cross this out. It's going to be F times D over 2 respectively. And then if we consider the shear stress, okay, failure tightly fit in figure 6.4, so the torque is equal to F times D over 2, and then the force is going to be equal to B times L times tau times D over 2, things like that, and we switch the side. Tau going to be equal to 2 times torque over B times L times D, things like that, 6.2. Highlight it, please. It means if we apply the torque there to the system, so therefore we be able to find the tau induced in the keys of equation 6.2 then. Okay, so we know automatically we just input the torque on that, so we find that the key induced in the key in equation 6.2 then. And then another one, see the tau there, because of course the key to tear us apart look like that into two pieces, look like that, okay, for the tightly fitted key. And then for in the case of another one, we just found consider the compressor's failure for the tightly fitted key. So we found that the torque going to be equal to F times D over 2. Okay, F is going to be H times L times sigma C there. So the sigma C is the compressive or the bearing stress anyway. So therefore, in this equation show us, okay, if we apply the torque there, again, we're gonna have experiencing compressive stress right there at the key, okay, equal to 4T over H time L time D respectively. So at the same time, 6.2 and 6.3 is going to be stress induced right there at the keys simultaneously. So typically, okay, if we equate x 6.2 equal to 6.3 equal to torque, things like that, so most likely, okay, maximum shear stress theory tau is equal to 0.5 sigma c, so therefore we have B equal to H. So if just like this is mean, okay, this one is very interesting. Let's say like this. This review that the key is B equal to H can be able to handle equal shear stress and compressive stress. It's good, right? So, however, when the stress concentration is taken under consideration, the square key may involve more and compared to a rectangular key into deeper keyway on the shaft. In addition, the corresponding strength of the shaft is less. But upon this reason, the square key is not quite widely used. However, it is used when the relative small shaft. Okay, if just like this, see? So the square key is not quite popular with the users with this the flat keys all the way. See, this is the reason. Okay, so because it's what you're gonna damage on the shaft rather than the good one anyway. So therefore, another one is if we torque the key and torque the shaft equal to each other, the L is gonna be recommended to be 1.757 T anyway. And then another one is recommended. See, this is going to be 3D, the pulley and the hub and the shaft and the keys thing together. So we apply everything together. We have the keyway from the head to the position, and we apply the keys on that. See, the key gotta be equal to the hub length. Okay, L. Okay, the hub diameter is gonna be D, the capital D, and the hub length is L all the way. See, so therefore the rule of thumb, number one. Okay, however the key length has to be considered based upon these corresponding features. Okay, number one, The key length value is typically determined from equation 6.2 and 6.3, and the longest key length will be used. So therefore, if I write up an equation, L longest determined from equation 6.2 or 6.3, we're gonna determine using the L longest one. Okay. Number two, the key length L should be equal to the hub length L. So if just like this, see, L should be equal to L, capital L, right? So in easy manner, when we take assembly, the key out of the pulley. So for the easy manner, easy operation, easy of assembly, disassembly, things like that, L should be equal to the capital L then, okay? And then if L is less than L should be equal to the capital L. So if the design key length is longer than the hub length, L of two keys located at 180 degrees apart on the shaft should be employed. So I just write down if L is greater than L, two keys each, okay, employ at the top and at the bottom of L equal to L. Then, okay, employ like that. Okay, so therefore this is the thing. And then another one, the typically the estimation of most common hub dimension. Okay, so hub dimension is very widely, okay, it's based on this their own manufacturers anyway. Typically the hub diameter based on the cast iron and then the mild steel, things like that. See, typically the hub diameter made of the cast iron, it's gonna be some kind like pullings all the way. So for the mild steel, it's gonna make up the gears, things like that, all the way. See, so therefore, typically this one you may write down for the cast iron. This is gonna be the pulley all the way. See, but this is gonna be the gear, whatever, all the way. So therefore, the types of the key is general. Okay, the things that what we mentioned. The spine is gonna be the things that what we're gonna talk it more. Okay, spine is gonna be so many keys. The Japanese machine use a lot of spine, things like that. The fader key, things like that. That what I mentioned to you already. We fix up the screw on the key, things like that to the shaft, whatever. The key does allow the axial movement of the hub along the shaft. So this means we allow the movement of the hub along the shaft, things like that. Okay, this is things that what we have got it right here. Okay, and then for example, okay, 6.1. See a shaft diameter of 75 is fixed with the pulley and key. Used to transmit the torque of 7,400 to drive in a compressor. Given the key and the shaft are made of 1020 CD steel and the safety factor of 3.5. Design the corresponding square or rectangular key for this transmission system. Okay, so therefore the shaft and the key are made of the same material. So therefore I got sigma y, sigma CD is going to be equal to sigma y over n, and tau design is going to be 0.6 CD then. Okay, so therefore this one, because that's why see this one, because of why see the key itself is very short there, so therefore we consider to be a single stress anyway. It's going to be simple stress all the way. So therefore, based on table 6.1 with the D of 75, I just make a selection of the diameter of square key is gonna be some kind of rectangular key of 20 times 12, things like that. So I just follow up the sequence of the design. See, I find the length of the key by equation 6.2 and 6.3. 6.2, I got L of 147. I got L of 6.3 is 295. So I get the longest 295. So therefore I look up in table 6.2, okay, and made a pulley. So pulley is made of cast iron all the way, right? So cast iron, I got make a selection of cast iron. It's gonna be on this table all the way. It's general key, right? So I got this one. It's gonna be 2.0 to 2, things like that. I make the middle, so that's why D is 1.557.5. So that's why the length I got 1.6 to 2. See, I set in the middle. It's 135. Okay, 135. I got 295. is going to be longer than L, right? So I'm going to apply two support, one at the top, another one at the bottom. So I got obtained 270. It's not enough, right? So therefore, this one is not correct. So I got to make a selection one more time again. So next time I gonna use the same thing, but now I use L is longer. It's gonna be 2 times D. It's gonna be 150. 150 times 2 is gonna be 300. So I need 295. So that's why it's safe for me to I just need 295 at least. So that's why I need 300. That'd be fine. So the correct answer is gonna be I just design with the keys up to rectangular keys with 20 times 12, okay, one at the top 150 millimeter, down under is 150, another one, and then I check with the stress right there. I got the tau induced in the keys there. I found the allowable stress is going to be 66 point something. So that's why the tau is less than the tau design. So my design is okay then. Okay, this is the things. Okay, that what I got it. Okay, there. So therefore, I I like to show you up there. So therefore, I want to go for for the second one, 6.2 example. It's pretty long one anyway. This is a typical type that what I liked it anyways for the real figure of that. 6.2, a solid shaft is made of steel 1020 with a Ka of 0.73, and then use transmit from the engine to the belt and pulley by the clutch as shown below. The pulley weight of 1,400 and the shaft is profile key weight. The belt tension is 1,200 and 200 respectively. We're gonna use the Soderberg criterion with the maximum shear stress theory to design the size of the shaft, and B is we're gonna use a key made of steel, and then the hub diameters of 120 with the hub length of 70. Okay, you design with a rectangular key, and see if the wood draft key is preferred. So therefore, we would like to design with the wood draft key. Okay, so the system going to be look like that. So figure A, see, we have done on that already. So that's why in chapter 4, you can look up in it. Okay, we come up with the answer of the diameter of 35. Okay, so therefore, for the square key or rectangular key, okay, I just look up the steel there. Sigma y is 390. The tau sub y, of course, this problem set is the combined stress, of course. But since the key here is very short, okay, is subjected to bending moment, okay, also. But since the bending moment is have no effect on the system at all, so therefore I just consider to be only the tau induced, only one simple stress. So therefore I think about only simple stress induced inside. So I just only think about simple stress. So that's why I just estimate the tau of y equal to 0.6 sigma y respectively. And then the tau design and sigma design, I find it automatically. Based on the table 6.1, I got the shaft diameter already, and then I find automatically the size of the rectangular keys. So therefore, since the subjected torque is going to be 60, so therefore I follow up the regulations of the design of the keys. So sequences, I find the L term. The longest L is going to be 4 point something. Since I found in the things that given by the problem set, I got the pulley is available with the length of the pulley is 70s, and then the hub diameter of 120. So that's why no doubt about it. I'm gonna use the length of 70s. Okay, millimeters. So therefore, I use the length of 70, no doubt about it. So I check the town design, okay, five only. So this is why the town design, the town is only 100, of only five. The town design is 117. So that's why it's safe anyway. So therefore, the wood drive key is preferred. So that's why I find the sigma y, I find the towns of y, and then I look up in the table 6.1. I got all dimensions there. I find the distance of AB up there based on the trigonometries. I find AB is 23.24. And then I find the torque max is equal to torque min. I find the AS, the stress area. See, the shear stress area that what I got there. So therefore, I find the safety factor is going to be 31 something. So you may figure out there, see, it's going to be very high in the terms of safety factor there. So the wood draft key gonna be pretty very safe anyway. See, and then for the keys and the hub, and again, see, I find the sigma compressive stress that what I've got there. I got the n is going to be 17 something. Okay, so therefore, in this kind of sense, see, you may figure out there. See, the wood draft key is going to be the keys that impart a lot with the German machines anyway. See, so therefore, this is the things that, for example, for the wood drive key. Another types of the key is going to be the standards of the SPI. SPI is going to be many types of keys anyway, like in the figure shows up there 6.6 in figure A. See, that's gonna be male, external spy, things like that. See, we have many keys, things like that. We have a female in B, things like that. Male and female spying gonna be according numbers of them equal to each other, things like that. So therefore, we have 4 T's, 6 T's, 10 T's, and 16 T's, respectively, for the number of spine, things like that. And then figure 6.4 and the type of spine, we have small spine and medium spine, things like that. So therefore, see in figure in table 6.4 show you some of the things that what we typically do on the selection of the spine. Many type of spine, okay, of the Japanese machine have been used a lot of spine anyway, because it's why spine in Thailand is not quite popular, because it's why we just scare, or we not very popular. We kind of lack of the technology in terms of machine hardening process on the steel, things like that, for the process of make the spine to be hard, things like that. Okay. So therefore, this kind of thing, we have small spine, C, and Z term here is going to be number of spine, and D is going to be the diameter, okay, the capital D there, okay, and then B is going to be the, 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 the width of the spine, things like that, okay. So therefore, this is the thing that what the medium and small spine going to look like. And then design of spine, things like that. See, it's going to be rather have a significant effect on the sigma c, because it's why we got a lot of assembly in terms of sigma z, because it's why we have so many numbers of spine, things like that. So therefore, the most likely damage is going to be in the sigma c anyway. That's why we have the more numbers of spine rather than the failure in terms of towns anyway. So another way around to the length of spine is going to be the most likely determination of the design. Anyway, we just make a cross multiplication. We got an L term, look like that. So therefore, this is a typical type of the design. Example 6.3 is going to show you some of the design of the lengths of the spine, things like that, and what we need to do for fabrication, things like that. Okay. So we have a problem set to show you some of practices, things like that. Number one there, show you some of the things that what we're gonna go for, some kind of design on the key, spin, and spine, things like that. Number two is going to be another one, very long one. And number three, another one. We have three problems set, so I would like you guys to do number one for me, okay? And submit to me as a homework assignment for me, okay, please, okay? So I'm gonna stop for my lecture for chapter 6 anyway. Okay, thank you. Okay, stop it then.